Yep, it is recording. Good. Conservation of linear momentum. It says if the net force, if all the force is being canceled, the net force acting on an object is zero. That means they cancel each other out. Its momentum is conserved. What does that mean? That means the linear momentum before the initial one equals the final linear momentum. Again, for this to be true, that means the net force acting on that has to be zero. Keep that in mind. If it's not zero, then it's not conserved. So here's an example. What are we going to use? Let's say you're in a... Where are we going to put you in? Bumper cart. That's the bumper. There's the people here. This one has 3 people in it. Mom and dad and a little child. And there's another bumper cart right here. They're stuck. You know, when you go racing, sometimes you get to a corner, you're stuck. This one has only one person. And now you're going to free each other. I guess, so you reach in, you push on them, and they push on you. So initially you're stuck, you're not moving. So if you go and you push on them, so this cart will go which way? In that direction with the velocity. And this cart will go in this direction with a different velocity. We'll number the cart. This is cart number 2. This is number 1. So we'll call this V1 and this is V2. Obviously the masses are not the same unless this person weighs 3 times, the 3 of them put together. So the mass of this we'll call it M1, the mass of this M2. Now when you get stuck there in that corner that you were making a turn, you're trying to pass them, somehow you get stuck and now you stop. If you stopped, what's your initial momentum? This one is not moving, that one is not moving. 0. Your initial momentum is equal the mass of the first one times the velocity of the first one, which is 0, plus the mass of the second one times the velocity of the second one, which is 0. You're stuck. Here's the 2 bumpers. This is that the bigger one, this is the little one. They're stuck right here. Now I'm sitting in this one. I'm going to push that one. Well, if I'm pushing on that one, and Newton's third law says what? This one's also pushing back on me. How much of a force? Equal and opposite. So when you add them together, what's the sum? 0. There is no net force. So I'm pushing, but this one's pushing back on me. They're canceling each other. So the net force is 0. So if the net force is 0, we have conservation of linear momentum. The initial momentum should equal the final momentum. Well, what's the final momentum? Well, let's define this direction is positive and this direction is positive. So for this one, for the first go-kart here, what's the mass? M1. And what's the velocity? V1. And what about the second one? What's the mass? M2. And what's the velocity? Negative V2, right? Because it's going which way? To the left. So you end up with 0 equals mass 1, velocity 1, minus mass 2, velocity 2. If you move that to this side, so if we think about them, if we said, okay, if the mass of this equals the mass of that, if the masses were equal, what about their velocity? If the masses are equal, would be the same, right? If the mass of this, a third of it, what's the velocity of this will have to be? 3 times, yes. The velocity of this will be 3 times the velocity of that. If the mass of this, half the mass of that, the velocity will be double, because it has to be constant. They have to equal to each other. I mean, we can put numbers there. So, okay, let's assume the mass of this is a third of the mass of that. So this is 1/3 m. This is m times v1. Notice the m's cancel each other out. It says velocity 1, this velocity, will be a third of this velocity, or velocity 2 equals what? 3 times velocity 1. Let's take another one. So we did this problem. We can give them some numbers if you want to give them numbers and see what will happen, you know. Another example we can use that NASA. NASA is a good example, actually. When we send people to the moon there, once actually we're orbiting the Earth in any of these orbits, they shut the engine. Because by itself, you're traveling about 17,000 feet per second. That's the speed. So you got a spaceship that looks like this. That's if you watch Apollo 13, that movie. They were living in that. Then they had the little piece of the end here. They had to go through this door, and this is the one they come to the Earth with, that little piece there. Once they decide it's time for them to come to Earth, they all go to that one, they lock the door, and they sit in that one. A little explosion will happen here to separate the two pieces together. This will go backward, this will go forward, and they come to Earth. So let's give them some numbers. Let's say this mass of this payload, that's what the big one is, has a mass of 2,000 kilogram, has a lot of equipment in it, has a food, has all the stuff they need for the next 6-7 days. This one is a smaller one. The mass might be 500 kilogram. And they're really, the engine is off, the two of them moving, but relative, like if I was another spaceship next to them looking at them, to me they don't look like they're moving, because everything in that orbit moves at the same speed. So right now, to me, you're not moving, right? We know that's not the case. The Earth spins around its axis, right? So something is moving, but to us, nothing is moving. To them, nothing is moving. So the velocity here is 0. We'll call that mass 1. V1 is 0 initially. And this is 2, and V2 is 0. That's the initial. Now they decide, okay, it's time for us to hit the Earth. Little explosion will happen here. This big one here, 2,000 kilogram, is going to travel in that direction. And this little one, well, it could go forward actually, but usually what happens, it goes backward, you know, in relation to that one. This one goes forward. We'll call it V2. Let's assume the velocity going backward for this, it's not a big, because it's not a massive explosion there. It's 2 meters per second. How fast this one's going to be going forward? Again, when the explosion happens, it pushes on each other. This one pushes back, this one pushes this way, they cancel each other, then the net force is 0. Just like the canoe. P initial equals P final. Let's assume this is the positive direction. That's the positive direction. So you won't go in the y direction, you were just going in that direction.
So it doesn't matter if the weight of
The weight, which weight?
those to the 2000.
Oh, it's going to come in. You're going to see it.
No, the net, the net.
No, the force? No, the force has nothing to do with the weight. Just like when you're pushing a car. Your mass compared to the car is not even close. You're pushing on the car. It doesn't matter if the car is moving or not. The car is pushing back on you with the same force. When I push on the wall now of 10 Newton, the wall is pushing back on me with 10. The mass of the wall and my mass, two different things. And notice, actually I just realized this, the chair moves. The wheels now, the friction force is not strong enough to keep me. Now if I use a chair that doesn't have wheels on it, if I push just lightly, you know I'm not going to move. Nothing to do with this subject. The reason is the friction force between the floor and the seat is keeping me from sliding backward. But this one has wheels. The minute I push on it, it doesn't take much to move me. Yeah. What's my initial momentum here? The mass, which is 2,000, times the velocity, which is 0, plus the second mass, 500, times the velocity, which is 0, equals. That's 2,000 at 200. And what's the velocity? Try again. What is it? Negative 2. Plus the 500 times the velocity v2. $4,000 equals 500 V2. I know what the answer is going to be. Remember, this is what? A fourth of this one? The mass of it, a fourth of this? The velocity of this is going to be 4 times that number. I guarantee you it's going to be 8. It's proportional to the mass. So if the mass of this, a fourth of that, then the velocity of this is going to be 4 times, because there has to be a constant. It has to be the same number. So if this is 1/4 of this, then the velocity has to be 4 times to make sure it compensates for that difference. Or 8. 4 times that number.
So that is 4 because 500 times 4 is 2,000.
Yep. 500 times 80 means 2,000. Oh, this one? Yeah. This number, when you 500 times 4 will make it 2,000. So this value, it's 4 times that. This velocity has to be 4 times this one.
Okay.
Yep. We always tell people, if you're on a pond and you're stuck and you can't skate, and you just happen to carry your physics book with you, take the physics books and throw it any direction. Because if you throw it that way, there's a force to push in that direction. Guess what's going to happen? For every action, there's an equal and opposite reaction. There's a force going to push you in that direction. The reason you can't move because there's no friction there, frictionless, between your skate, if you have skates on, and the ice there. It's frictionless, so you're going to slide and keep sliding. If there's no friction, keep moving all the way till you get to the shore. The truth is nothing is frictionless, you know. So you might go about 2 feet, then you get stuck again, you know. But if it's ideally frictionless, that's what you do. So it doesn't take much of a force to get you keep going all the way. Like if there is no friction there, this actually rocket will keep going all the way in that direction. So the same idea, that book there, but we'll use somebody in the pool here. There's the pool, lake, whatever you want it to be. Private lake, the pool might not sound like just swim to the side, you dummy. But somebody in a lake there, water there, big lake, on a piece of wood, raft, whatever you want it to be. So there's a person standing on that one, on that lumber there. It's a lumberjack guy, I don't know, 61 kilogram or 60 kilogram, doesn't make a difference, 61 kilogram. The log itself has a mass of 320 kilogram. The show on TV, these guys go logging in the water. They find all this wood and take it. So he finds that log in the water. He's like, oh, that's a nice piece of log. I need to get it back to the shore. So let's see. Doesn't have a rope, nothing. He swims to it. Oh, nice rope. Now, how are we going to get it to shore? Let's assume both of these, nothing is moving. It's a lake, so the water is not moving. The velocity here is 0. The velocity of the man is also 0, initially. Now, what happens? The person wants to get the log to go in that direction. He starts running on that log, on top of the log, moving to the right with a speed of 1.8 meters per second. What's going to happen to the log? It's going to go to the left. Some velocity v. So let's see what's the velocity of the log there. Again, there is no net forces. The only forces is on that. The person sitting on the log, so has his weight down. But guess what? The log is pushing up on him. Normal force. The log is pushing down on the water with the weight. The water is pushing back on the log. They're canceling each other out. So the net force is 0. There's no other forces. It's not like he's a big guy and it's windy outside, the wind is pushing him. Nope, we didn't mention any of that stuff. Or has a sail with him and opened it. Nothing. The net force is 0, that means P initial equals P final. What's P initial? The mass, which is 61, times the velocity initially was 0, plus the mass of the log, which is 320, times the velocity, which is what? 0. This marker is dying. Seems like every day we kill a marker. Okay. The final. What's the mass of the person? 61. And what's the velocity? 1.8. Plus the mass of the log. Now, if I don't know which way the log is going to go, I can just go times v and let the math tells me if it's positive or negative. Because a lot of times you're not sure if the log is going to go forward or backward. How do you know it's going to go backward? You know? But if you don't know that, just make an assumption. I don't know which way it's going to go. Watch this. I'm going to make it going forward. I don't know. And say, you know what? That log, I think the log is going to go in that direction with the man, with the lumberjack. The math is going to tell me if I'm right or wrong. $109.8. That's a negative when you move it to that side. Can we get what V is? Negative. What does negative means? Which way is it going? Backward. So if you keep doing this for a couple of days, you might make it to the shore. You know? You're moving slowly. 0.3 meters per second. So just to give you an idea, if you did that all day, 0.3 meters times 60, you're going to move that 18 meters every hour just by walking. And you got to walk gently backward to repeat the process. It's going to move as you walk backwards. It's going to move, but just gently. It doesn't move that fast. And keep going, running to the end. Gently, go like this. Hop over, so it's not really moving backward. Then do it again. Come back. Then do it again. That means you're going to walk twice that distance, the log, because you got to go to the end and come back, end and come back to move each time. Yeah.
I think you should just push it from the back. Swim in the water. Lay down. Yeah.
Yep, you can lay on top of it and swim and pull it. Yeah. So that's really what conservation of linear momentum.